Okay, the first question is on the modulus of linear functions. This is the second bullet point from the advanced information. So we've got a modulus graph, y equals 2 times modulus of x plus 4 minus 5. Just a quick recap. For a modulus graph, so y equals to the modulus of x, the lowest point is at the origin 0, 0. And if you compare the equation here with the one given here, we can see that there's operation done inside and outside the bracket. So there's plus for inside, which means the origin has shifted to the left by 4. So it's now at minus 4. And on the outside is minus 5, which means it's gone down by 5. So the coordinate of point P will now be minus 4, minus 4, minus 5. So that's straightforward. For the next part, it says that 3x plus 40 equals to the graph, the modulus graph. Now the modulus graph, the right side is already drawn. On the left side, 3x plus 40, you don't need to draw that in, but I'm going to draw it in afterwards anyway, just to illustrate what happens when we solve the equations. The 2 here, what the 2 does is it just tightens stretches the modulus graph along the y-axis. The coordinate P, in terms of 2, it's outside the bracket, so it affects the y values. So the minus 4 isn't affected. Okay. Now the original coordinate, the y coordinate of the minimum point is 0. So if you times it by 2, it's still going to be 0. In terms of the 2, it doesn't affect the y coordinate, it just affects the x coordinate. So what the 2 does, if I illustrate again, if I stick a 2 in the front, so if I do y equals 2 times modulus of x, then what it does is it's going to make it more stretched out. Okay, and because there's no numbers on the axes, on the y-axis, there's no need for me to squash the graph along the y-axis. It just, the 2 only affects the stretch along the y-axis, doesn't affect the x values. So we're going to solve this equation now. So we've got 3x plus 40 equals to the modulus graph. Now the modulus graph has two branches. The one on the right is the positive branch, and the one on the left is the negative branch. So we can see that one on the right will have a positive gradient, one on the left will have a negative gradient. So we have 3x plus 40 equals to, take the positive branch, then we'll have positive 2 times the bracket x plus 4 minus 5. And if you solve that equation, so we get 3x plus 40 equals to 2x plus 8 minus 5. So that rearranges to x equals to 3 minus 40 is minus 37. Okay, so we get this solution. And so that's the positive branch. If we now do the negative branch, we get 3x plus 40 equals to minus bracket, minus 2 bracket, x plus 4 minus 5. So that's 3x plus 40 equals to minus 2x minus 8, and then minus 5. So that's 5x minus 53, and then divide by 5. So it'll be minus, you get minus 10.6. Now, looks like there's 2 solutions, right? Now we need to check, are both solutions valid, or is one of them invalid? Okay, so there's both solutions are negative. So let's look at the graph of 3x plus 40. Plus 40 means the y-intersection is going to be somewhere on the top. So let's say the intersection is here. If you look at the positive branch, the gradient of the positive branch, if you expand the bracket, you can see it's 2x minus 3. So the gradient of this line here would be 2. So the gradient of this positive branch, m equals 2. Now, the other line is 3x plus 40. Intersection is at 40. So it'd be a straight line going down like this, but the gradient of this line would be 3. So this line is steeper than this one here. So as this line goes up, so this line is steeper, so it gets even, it moves away from the line below. It's just further you go up, the top one goes upwards, the other one goes the other way, so they will never intersect going up. But if this line was to continue downwards, Now remember, we're looking at the positive branch. So the negative branch, we're now ignoring the negative branch for now. And if we extend the positive branch, eventually they will cross down below. So when they cross, the x value will be minus 37. But if you look at the modulus graph, the positive branch is only up until minus 4. So for the modulus graph, x really has to be bigger than or equal to minus 4. In which case, is that minus 37 going to be a valid answer? No. So in that case, this is not valid, because the positive branch intersects the line 3x plus 40 when x equals minus 7, which is way beyond the point where the minus 4 is, because the positive branch, if you look here, it only starts at minus 4 and it goes towards the right. Okay, so now if we now look at the negative branch and this line of y equals 3x plus 30 intersect the negative branch once, which is there. And the negative branch is for x values less than minus 4. No, less than equal to minus 4. And minus 10.6 is within range, so this is the only solution we get from this equation. You might say that, hang on, this question is only worth 2 marks. Do we need to show all these steps? Okay, it's not a show question, it just says solve the equation. So the only advantage here is if you have a graphical calculator, you can draw the graph and you can see that where the two graphs intersect, and you can see that there's only one point of intersection, which means it must be at minus 10.6, in which case you don't need the minus 37. That's not going to be a solution, a valid solution in this case, because the minus 37 is this intersection of the positive branch. So this one will go down, eventually will intersect with the other one, but that's outside the range of our values. Right, and the next part C. So line L has an equation y equals to ax. So y equals ax is intersecting our modulus graph at least once. Right, so y equals ax is a straight line. It has to go through the origin. So y equals ax will be a straight line that goes through the origin. So this will be the line of y equals to ax. So we want this line. So we want this line here to intersect the modulus graph at least once. So you can cross it once or twice. Okay. We can only make this happen by changing the gradient of the line, which is a. The question says find the range of possible values of a, and they give you the answer in set notation. So a could have a range of values. So when we change the values of a's, the gradient changes, and as it does, it may cross the modulus graph. So let's start from the point where it touches the modulus graph at point P. Okay, so here, at this very point, so this is y equals to ax. So at this point P, if that line crosses the point P here, what would be the gradient be? What's the gradient of this line here, where the graph crosses point P? So it crosses the origin, 0, 0, crosses point P, minus 4, minus 5. What's the gradient at that point? It's the difference in y over difference in x. So minus 5 take away 0 is minus 5, and minus 4 take away 0 is minus 4. That gives you 5 over 4, which is 1.25. So the gradient here is equal to 1.25. So when a equals to 1.25, how many solutions do we get? We get one solution, because it touches the modulus graph at the lowest point. Now what we're going to do is we're going to increase and decrease the a value and see what happens. I'm going to go by decreasing the value of a. But a is a gradient. What happens when we decrease the gradient? Does the line get steeper or less steeper? It gets less steeper. So if we now decrease the value of a, so let's say a is less than 1.25, the line is going to be like this. Right, so is that a smaller gradient? And then that's going to be even smaller gradient. Okay, until it's a flat line. So when it's a flat line, what's the gradient? Gradient is 0. Okay, so when a is less than 1.25, how many solutions do we get in each case? There's 2 solutions because there's 2 points of intersection. But what if we decrease it even more? So gradient is now 0. Decrease it even more. What's the gradient now going to be? What's less than 0? Yeah, it becomes negative. So if it's negative, the line is now going to be going down like this. Can you see if the line slopes down, it has a negative gradient. Up until, this is even more lower. So what's the lowest we can get it down to? So you can see from here that from this point, the line is literally turning this way. We're turning it clockwise to the maximum possible, well, the lowest possible gradient would be, the lowest possible number could be negative infinite. Okay, so in other words, if a is less than 1.25, do we get at least one solution? Yeah. So if you lower than 1.25, no matter how low you go, the line is going to always cross the modulus graph at least once. So when it's equal to 1.25, we get exactly one solution. When it's less than 1.25, we get 2 points of intersection. That's what happens when you go clockwise. But now let's go the other way around. See what happens. So I'm going to rub these bits off. Okay, so let's get our original line in. So this is the line where it was 1.25. Okay, but now if we were to move away from that gradient in this direction, anti-clockwise, the gradient is increasing in that case because the line gets more steeper. As we make it steeper, it moves away from point P, so straight away there's going to be no solution. Up until the line is exactly parallel. When those two lines are parallel, will they ever meet? No. So what would the gradient of my line be when it's parallel to the modulus graph, the positive branch? Can you see what the gradient is here? So when the gradient of y equals ax equals 2, we'll have no solutions. But what if the gradient was more than 2? Would it then intersect the positive branch? Yeah, it's going to intersect. In this sense, a has to be more than 2, more than the gradient of the positive branch in order for y equals ax to intersect with this, up until the biggest possible gradient we see when it's vertically going up. So that's the other range of values for a where we get at least one solution. And we need to show this using set notation. Okay, so using set notations, all we have to do is say that a is such that a is less than 1.25. So that's one set of values. And then we say a is such that a is bigger than 2. That's another set of values. Okay, what goes in between? Well, can you have a number that's more than 2 and less than 1.25 at the same time? No, so it's not an intersection. It's going to be a union. So it's one or the other. Right, so that's question part C done. Question 2. So what we have here is a function given piecewise. So for different values of x, the graph behaves differently. So this point here is x equals 2. So when x is less than or equal to 2, we have a quadratic graph, which is the left side. When x is more than 2, we have the right side, which is the linear graph, 4x minus 7. Okay, so first part, we're going to work out g of 0. So to work out g of 0, well, 0 is less than 2, so that goes inside the top one because 0 is less than or equal to 2. So you substitute it into the quadratic one. So that's 0 minus 2 squared plus 1. That gives you 5. So then that goes back into the g. But now the input is bigger than 2, so we use the linear one, which is 4 times 5 minus 7. So that gives you 13. So therefore g of 0 equals to 13. For the second part, g of x is bigger than 28. So for g of x to be bigger than 28, the g of x graph is drawn there. So the left side graph is already drawn. The right side is the graph of y equals to 28. So if you draw the graph of y equals 28, it's going to be a horizontal line intersecting the g of x graph. So this is y equals to 28. This is the point of intersection of both graphs. So let's say suppose we knew what these points were. So we had the x value here and we had the x value here. Now the inequality is showing us that we want the g of x graph to be above the y equals 28 graph. So our g of x is above the 28 graph for x values which are towards the right side of the point of intersection. The g of x graph here is above the red line for these x values, and our g of x graph is above the red line on the left side for x values on the left side of the point of intersection, which is on the left. So to work out the solutions to this, to find all the values, first we need to figure out the point of intersection of the two graphs. So to find point of intersection, we just have to equate them and solve the equation. Just like in one of the questions you had in the PM1 paper, you had two graphs C1 and C2. Where do they intersect? Well, you just equate them and solve the equation. So here, if you look at the left side is the quadratic branch intersecting the line y equals 28. So we're going to make x minus 2 squared plus 1 equals to 28 to find that point of intersection. So x minus 2 squared equals to 27. So x would be 2 plus or minus root of 27. Now there's two solutions. We get two solutions with the intersection of the left branch. But if you look at the domain of the left branch, x has to be less than or equal to 2. So do we need 2 plus root 27, or do we need we need 2 minus root 27 in this case? Because x has to be less than 2, which is on the left side, we need 2 minus root 27, not the positive one. So there we go. So the intersection on the left is 2 minus root 27. And the g of x is above 28 for x. And if you look at the arrowhead, x is less than 2 minus root of 27. Root 27, obviously, you can simplify. Now on the right side, we are intersecting 4x minus 7 with 28. So 4x is equal to 35. And 35 divided by 4, x equals to 8.75. So here we can write 8.75. And you can see here that when x is bigger than 8.75, the graph is g of x is above the red line. So we need x to be bigger than 8.75. Okay, it's not asking for set notation, so we can just leave the answer using inequalities, because that expresses all the values where this is the case. For part C, h of x is given as the quadratic part of our g of x when x is less than or equal to 2. Explain why h of x has an inverse but g of x does not. So what's the criteria to have an inverse function? Yeah, it has to be 1 to 1. A function only has an inverse if it's 1 to 1. Our h of x, if you look at h of x is a quadratic graph. Let's quickly do a quick recap on quadratics. So that's the x squared graph. The x squared graph is a many to one function because the two different x values give you the same y value. But if we were to restrict the domain of our quadratics, let's say x is more than or equal to 0, then this branch gets crossed out. And then from a many to one, it turns into a 1 to 1 function. So we can turn a many to one into a 1 to 1 by restricting the domain, by cutting off the domain. So that's exactly what's happened to this quadratic here. So you can see here that x is limited to 2 or less. As you can see from the graph, that for x less than or equal to 2, the quadratic is just one branch of it. So h of x is therefore a one-to-one function. And g of x, you can see here that we've got two different x values giving you the same y value. So g of x is many-to-one function. So that's the reason why h of x has an inverse and g of x doesn't. And for question D, h inverse of x equals to minus a half. Okay, so there's different ways of working this out. You can actually work out the h inverse function and then equal it to a minus a half, and then rearrange and solve the equation. Or another way of looking at it is that just knowing how what a function does. So the left side is the domain, the right side is the range. Right, so the domain contains the x values, the range contains the y values. Function h takes the x value and changes it into the y value, whereas the h inverse function, the inverse function's job is to take the y value from the range and give you back the x value in the domain. If we're told that h inverse of x equals minus a half, it means that the y value, what y value do we get when the x value is minus a half? So the output of the inverse function is minus a half. So the output given here is the x value. So the output of an inverse function is giving you the x value. It takes the y value and it changes it back into the x value, and that value is minus a half. So if h inverse of x is minus a half, it's actually giving you the input value of the original function h of x, and what we need to work out is the y value. So where do we substitute minus a half into then, in that case? Into h of x, into the original function. So therefore the answer to this would be h of minus a half. So sub that into your equation. So that's 5 minus 5 over 2 squared plus 1, you should get 7.25 for the answer. Right, question 3, binomial expansion. So the binomial expansion formula is given in the formula booklet. So 1 plus x to the power n is approximately equal to 1 plus nx plus n minus 1 x squared over 2 factorial plus the other higher powers of x's. But you can see from here that we are only expanding up to the quadratic term of the expansion. So what we have is the root of 1 plus 4x over 1 minus x, which we can rewrite as bracket 1 plus 4x to the power of a half times by 1 minus x to the power of minus a half. So these two themselves will expand into two more brackets using the binomial expansion, and the final two brackets need to expand together and give me 1 plus 5 over 2x minus 5 over 8x squared. That's what we need to show. Right, it's a show question, so we need to show how we get to this expression here. So let's start with the expansion of 1 plus 4x to the power of a half. So in this expansion, we're saying that n equals to a half, and x has been switched with 4x. So that's approximately equal to 1 plus nx, so that's a half and times by 4x, and then n minus 1 times by the 4x squared divided by 2 factorial, which is 2. Let's simplify this, so we get 1.5 times 4, so that's plus 2x. I would say that if you're not confident in working with arithmetic with fraction, just type it all in the calculator. Just remember that when you're calculating for the bracket one being squared, make sure you use brackets and the power, close the bracket and then square it to get the coefficient. So a single negative, so this would be actually a negative value. So you got 2 times 2 is 4, cancel one of those 4's off, 4 over 2, so you get 2x squared from that. And then we do 1 minus x to the power of minus a half, so n equals minus a half, x switched with minus x, so that's approximately 1 plus minus a half times minus x, and then minus a half minus 3 over 2 minus x squared divided by 2 factorial, which is 2, equals to 1 plus a half x. I got 4 minuses, so it's a plus, and that's 3 over 2 times 2 times 2, so that's 3 over 8 x squared. So what we now have is those two now are multiplying each other, so let's write them side by side. So we have 1 plus 2x minus 2x squared multiplied by 1 plus half x plus 3 over 8 x squared. So we're going to do 1 times 1, 1 times a half x plus 1 times 3 over 8x squared. Then we do 2x times 1, 2x times a half x, which is just going to give you x squared. And then 2x times 3 over 8x squared is a higher power. It's a cubic one, so we're going to ignore that. And then we do minus 2x times 1, which is minus 2x squared. And minus 2x squared times the others, it gives you cubic and plus, so we're going to ignore those. So tidy this up. So we got 1 half x plus 2x gives you 5 over 2x. And then we got 3/8 of x squared plus x squared minus 2x squared. So 3/8, and then take away 1, gives you minus 5/8. So minus 5 over 8 x squared, and we have the expression required. Now, going back to the formula, the original expansion at the top is only valid for the modulus of x less than 1. Question B says, give a reason why we shouldn't use x equals a half. Well, it may be valid for the original formula where modulus of x is less than 1, but for our expansion, we said that x is equal to, or x is switched with 4x. So the modulus of 4x has to be less than 1, which means the modulus of x has to be less than a quarter. For the second expansion, this is what we said, which means the modulus of minus x is less than 1. That's the same as saying modulus of x is less than 1. But for both expansions to be valid, we take the smaller one. So for both of them to work, x has to be less than 1/4. So for question B, where it says give a reason why we can't use x equals a half. Well, a half is more than a quarter, so it's not inside the range of values where it's valid, so therefore the expansion will not be valid. And then for question C, substitute x equals 1 over 11 into the expansion, into this expression to find an approximation for root 6. Well, if we just simply plug it into the left side, so the left hand side is the root of 1 plus 4x over 1 minus x. If we just simply calculate, put that into our calculators, that should give you root 6 over 2. And this has to equal to the right side, which is your expansion with x equals 1 over 11 substituted in. So it'll be 1 plus 5 over 2x, which is 1 over 11 minus 5 over 8, and then 1 over 11 squared. I would say show this substitution. Okay, so don't just plug in the calculator, give an answer, and just in case you get a wrong answer. By showing the substitution, you will at least get a method mark if that's available. So root 6 over 2. Now you can plug it into your calculators. Don't forget to use a bracket for the last one, and close the bracket and square it. I'm getting 1183 over 968. Therefore, root 6 would be this fraction multiplied by 2. And we should get 1183 over 484. Now, just to check what the decimal value is it to that. And if you subtract root 6 from that, what do you think we should get a number close to? So if you take this fraction, and if you take away root 6 on the calculator, what should you get close to? You should get close to 0. And if it doesn't, then that's a hint that, you know what, I've gone wrong somewhere. I have to go back and do my workings again. That's a quick check you can do, because if it is approximation root 6, then if you subtract root 6 off, we should get close to 0. Right, question 4. This one, series generated by an iterative formula. So here's one of those types of questions. So in this sequence, we're given that the sequence has a period of order 3, and the first term is equal to 2. So I'm going to use the space here. So given that a1 equals to 2, a2 is going to equal to k times the bracket, the previous term, which is 2 plus 2 over 2. Now it's very important that you simplify each term before you substitute it into the next one. Otherwise, it's going to get very complicated if you don't simplify. So that gives you 4 over 2. So that just gives you 2k at the end. So a3 would be therefore 2 times the previous one, which is 2k plus 2 over 2k. Again, expand. See if we can simplify this. So that gives you 2k squared plus 2k over 2k, which we can simplify. Well, I guess you didn't have to expand. You can see from here that you can cancel the k off, and then we can just divide everything on the top by 2. So that just will give you k plus 1 when you simplify. Now, I've got to mention that an order 3 sequence means that once you get to the 4th term, it takes you back to the first term. So the 4th term will be the same as the first term for a sequence of order, periodic sequence of order 3. So we worked up to the 3rd term. So now we need to find an expression for the 4th term and equate it back to the 1st term, and then that should lead you to this quadratic here. So we have k bracket k plus 1 plus 2 over k plus 1. Simplify that, so that's k bracket k plus 3 over k plus 1. And we're now going to make that equal to the first term, which is 2. So rearrange. So we get k bracket k plus 3 equals to, then take that across and multiply. So that's 2k plus 2. Expand the bracket. K squared plus 3k equals to 2k plus 2. Therefore, k squared plus k minus 2 equals to 0, and we have that expression. For the sequence, explain why k is not equal to 1. Well, let's see what happens if k equals to 1. If k equals to 1, then the first term would be 2. The second term would be 2 times 1, which is 2. And the third term will also be 2 because it will be k plus 1. 1 plus 1 is 2. So what we're really getting here is a sequence, is a periodic sequence of order 1 and not order 3. So that means that, because it's a problem, because our sequence has to be a periodic sequence of order 3. So in that case, k therefore cannot be equal to 1. So why is that useful? Because the quadratic equation we have has 2 solutions, and maybe k equals 1 is one of them. So that's where the second part, part C, comes in. So you want to find a range of values for from r equals 1 to 80 of AR. So what that basically means is you're doing A1 plus A2 plus A3 plus all the way to the 80th term. Now, luckily for us, it's in order of period 3. So we know that those 3 triplets will repeat over and over again up until 80, and then obviously may get a few extras at the end, which may not make it a full triplet. Now, what are the terms? So to work out the terms, obviously we need to work out the k values. So let's solve the quadratic equation first. So k squared plus k minus 2 equals to 0. So this factorizes into k minus 1, k plus 2 equals to 0. That gives you k equals to 1 or k equals to minus 2. But we know from part B is that k can't be equal to 1, so we need to have k equals as minus 2. So then we get the first term as 2. The second term is 2k. K is minus 2, so 2 times minus 2 would be minus 4. And the third term is k plus 1, so minus 2 plus 1 equals to minus 1. So if we now add the first 3 terms, a1 plus a2 plus a3, that's 2 minus 4 minus 1 minus 3. So first 3 terms adds up to minus 3. So how many of these do we have up to 80? Well, if I do 80 over 3 and change that into a mixed number, you should get 26 and 2/3. So what that means is that we've got 26 lots of minus 3s. So the summation from 1 to 80 of AR would be 26 lots of minus 3 plus 2 out of the 3 terms. In other words, the first 2 terms plus A1 plus A2. A1 is 2 and A2 is equal to minus 4. So we add those on to this. So 26 times minus 3 is equal to minus 78. Then we got plus 2 minus 4. So the final answer is minus 80. Right, so question 5, the use of a trigonometric function is using in modeling type questions. So this is a quite common question where we have to use the R alpha method to turn the sum of 2 trigs, sines and cos, into a single trig function. Right, so the first part, express sine x plus 2 cos x in the form r sine of x plus alpha. So I'm just going to use the addition rule for this and open this up. So this will be r sine cos plus r cosine. Okay, so the addition rule is given in the formula booklet. Sine of a plus b is sine cos plus cosine. Now, if we compare the coefficients in this, so r sine alpha, so r sine alpha is the coefficient of cos x. Cos x on the other side, coefficient is equal to 2. So r sine alpha will match with 2. So r sine alpha equals 2, must equal to 2. R cos alpha will be therefore the coefficient of sine x, which is 1. So r squared would be equal to 2 squared plus 1 squared. Therefore r would be equal to the square root of 5. And if we divide this to get tan alpha would be 2 over 1, which is 2. So tan inverse, and we want it in radians. Radians to 3 decimal places, so 1.107 to 3 decimal places. That's our alpha. But the question asks us to express it in that form. So the final answer we need to give is what that expression is. So that's root 5 times by sine of x plus 1.107 would be the answer. Right, so the temperature inside the room is given by this function here. Now if we compare this to what we have here, okay, well, look at the sine and the cos bit. So the coefficients of sine and cos match, but the whole expression of sine and cos will match if we say that x is equal to pi t over 12 minus 3. If you do that change, then theta can equal to 5 plus this sine plus 2 cos, which we can rewrite as the square root of 5 times sine of x plus 1.107. So that's the new formula now for our theta. Only thing is the x has to be replaced with what we changed it into. So that's pi. Oops, I'm going to have to rewrite that bit. So it'll be sine of x plus 1.107, but x is equal to pi t over 12 minus 3, and then plus 1.107. So let's tidy this bit up. Right, so that gives you minus 1.893 to 3 decimal places. So that's our new theta function. Deduce the maximum. Right, so the maximum theta therefore is going to be 5 plus root 5. Sine is the only function that changes the theta value. So when sine reaches a maximum, which is 1 times root 5 is root 5 plus 5 gives you the highest value. Find the time when this maximum occurs. Well, when theta is maximum, theta is equal to 5 plus root 5. So we're saying this is equal to 5 plus root 5 sine of pi t over 12 minus 1.893. So we can cancel out the 5s and then divide it by root 5, so we get 1 equals to sine of pi t over 12 minus 1.893, and then do the sine inverse of 1 in radians. So sine inverse of 1 equals to pi by 2. So pi t over 12 minus 1.893 equals to pi by 2. Obviously we want the answer to be positive, so it looks like this will give us a positive value, so we don't need to figure out the next available solution. So if we rearrange and make t the subject, so that's just going to be pi by 2 plus 1.893, and then multiplied by 12, divide that by pi, so it's doing all that in one go. So pi by 2 plus 1.893 times by 12, and then divided by pi. We get 13.23 ... Okay, time is measured in hours, but we want the answer to the nearest minute. So just times up by 60 to do a conversion. It says time of day. So time of day means we need to use the clock time for that. So that means I'm not going to times the whole thing by 60. So we've got 13 hours plus the decimal hours. So we're going to subtract 13 off from the answer and then times by 60 to the nearest minute is 14 minutes. And if you look in the question, time starts after midnight. So after midnight, time therefore would be 1314 or 1:14 p.m. in that case. I'm skipping question 6 because I just realized that this topic was covered in the Pure 1 exam. So iteration using a turning point. So let's jump to question 7. So express as partial fraction, and then if you look at the second part, it's the differential equation. So because the partial fraction is involved in part A, it means that when you rearrange, you shouldn't get a partial fraction for the second part. So express as partial fraction, so we can write this as a over p plus b over 5 minus p. So in that case, 1 would be equal to a bracket 5 minus p plus b times p. Okay, so are we okay with the first part here? How to rearrange into this form? So that's equal to 1 over p bracket 5 minus p. You just take that and multiply onto the left side, and it cancels down into this. So if p equals to 0, right, we're just going to get 5a. So that means that a equals to 1 over 5. And when p equals to 5, we're going to get 1 equals to 5b. So b is also 1/5. So our partial fraction, therefore, is equal to 1 over 5p plus 1 over 5 bracket 5 minus p. Now, the team of conservationists is studying the population of meerkats on the natural reserve. The population is modeled by this differential equation, where p is measured in thousands. Population of meerkats at time t is measured in years since the study began. Given that t is 0 when p is 1, it's going to be useful for us later on. Solve the differential equation to get this expression here. Alright, so I'm just going to rearrange this one here. So, because dp is on the top on the left side, that needs to move to the left side. I'm going to leave the 1 over 15 behind, and I'm going to bring the dt across. So that will rearrange into 1 over p bracket 5 minus p dp equals to 1 over 15 dt. Now both sides are now separated. We can now integrate. And if you look at the fraction we got here, that's the exact same fraction we had there. So we can easily switch that into the partial fraction. So we can switch that into 1 over 5p plus 1 over 5 bracket 5 minus p dp equals to integration of 1 over 15 dt. Now to make the integration slightly easier, I'm going to factorize out the 1 over 5 from the left side. So take 1/5 out of the integral, and all we have is 1 over p plus 1 over 5 minus p dp. And if we now integrate this, this would be 1 over 5 bracket ln p minus ln of 5 minus p close bracket equals to the right side. We'll just integrate into 1 over 15t, and I'm going to introduce a constant here. Now, very important that we need this minus here, because can you see the minus p here? When you differentiate the denominator, you get minus 1, but we got a plus 1 on the top, so the adjustment needed is minus 1 for the ln. We can now substitute in for a boundary condition, which is 0 and 1. So we would get 1 over 5 bracket ln 1 minus ln 5 minus 1 is 4 equals to t. 0, that goes away, so that's equal to c. So c is basically going to be equal to 1/5 of ln of 1/4. ln 1 minus ln 4 is ln of 1 over 4. Hang on a second, but ln 1 is 0, so I can just make my c equal to minus 1/5 of ln 4. So my equation now becomes 1/5 of ln p minus ln of 5 minus p equals to 1 over 15t minus 1 over 5 ln 4. I need to now rearrange this and make p the subject. Right, so let's continue here on this place. We'll get rid of that fraction by multiplying everything by 5. So we have ln p minus ln of 5 minus p equals to 5 over 15 is 1/3. 1/3 of t minus 1 times the right side by 5 as well. So that fifth goes away. So we get ln 4. Ln p minus ln of 5 minus p, that just gives you ln of p over 5 minus p equals to 1/3 t minus ln 4. E both sides, so p over 5 minus p equals to e to the power 3rd t minus ln 4, which we can rewrite as e to the 3rd t times by e to the power minus ln 4. And then I'm going to raise that minus to the top here and cancel off the e and the ln. So this will give me e to the 1/3 t times by 4 to the power minus 1. So which is basically 1/4 of e to the 3rd t. So p therefore is going to be 5 minus p multiplied by 1/4 e to the 3rd t. So expand that out, so you get 5 over 4 e to the power 3rd t minus 1/4 e to the 3rd t times by p. I want to make p the subject, so I now need to move that p term to the left, add it on with the other p. So p plus 1/4 e to the 3rd t p equals to 5 over 4 e to the power 3rd t. Factorize the p out. And then divide across by the bracket. So p therefore would be 5 over 4 e to the power of 3rd t over 1 plus 1/4 e to the power 3rd t. Now if you look at the final expression, the e only appears on the denominator and it has a negative power. We can easily make that happen by timesing the top and bottom by e to the power of negative 3rd t. So if you simplify that, the top, the e cancels off, so we get 5 over 4 on the top. And we have e to the minus 3rd t plus 1/4 times e to the 3rd t times e to the minus the 3rd. The e cancels, so we just get 1/4 back from that. Okay, but here it says that the constants needs to be integers. So to be integers, I just need to times top and bottom by 4 to get rid of the fractions. So we get 5 over 1 plus 4 e to the power minus a 3rd t. Hence, show that the population never exceeds 5,000. Just do it in that little space here. As t goes to infinite, so as t goes to infinite, e to the minus t goes towards 1 over infinite, which is 0. So the negative power of t, exponential part, goes to 0. So e to the minus 1/3 of t turns towards 0. So p therefore is going to turn towards 5 over 1 plus 4 times 0, which is 0. In other words, p will turn towards 5, but p is measured in thousands, therefore p will turn towards 5,000, hence p will never reach above 5,000. Alright, so the equation 2x cubed plus x squared minus 1 equals 0 has exactly one real root. Show that for this equation the Newton-Raphson formula is given by this expression. Right, so the Newton-Raphson formula, xn plus 1 equals to xn minus, so we can see from here that f of x equals to 2x cubed plus x squared minus 1. f dash of x equals to 6x squared plus 2x. So we just have to substitute this into the formula. So xn plus 1 equals to xn minus fraction f of x. So x we're going to obviously make it as xn for all the x's. So the top would be 2x cubed plus x squared minus 1. Underneath is f dash, so it'll be 6x squared plus 2x. If you look at the answer, it's given as a single fraction. So we need to rewrite this as a single fraction. So I'm going to cross multiply. So it'll be xn bracket 6x squared plus 2x minus 2. Again, this minus is minusing the whole fraction, so this be inside a bracket. All over 6x squared plus 2x. If we expand the bracket, we get 6x to the power 3 plus 2x squared minus 2x and to the power 3 minus x squared and then plus 1 over the same denominator. So that simplifies to 6n cubed minus 2n cubed is 4xn cubed plus xn squared and then plus 1 on the top over 6x squared plus 2x. And this is the iteration formula that comes about from applying Newton-Raphson. So this matches the formula given here. So this is a formula that is used for the question on the top there. So now we're going to use the iteration of x equals 1 into this formula to work out the second and the third estimations to the solution. So x1 equals to 1. X2 would be just showing the substitution, plus 1 squared plus 1 over 6 times 1 squared plus 2 times 1 gives you, that should give you 3 over 4. And then for x3 it will be 4 times 3 over 4 cube plus 3 over 4 squared plus 1 all over 6 times by 3 over 4 squared plus 2 times 3 over 4 should give you the answer 2/3. Right, okay, and the final bit of this, part C, explain why for this question the Newton-Raphson method cannot be used with x equals 0. Well, if you look at what happens when x equals 0, so when x equals to 0, if you look at f dash of 0, we've got the f dash here. If you sub in 0 into f dash, you're going to get 0. In other words, the gradient is 0 at x equals 0. So what we have at x equals 0 is a turning point. So we quickly draw a diagram to illustrate what happens at turning point and why the Newton-Raphson doesn't work. So let's say we've got a curve like this. It crosses the x-axis at that point. So this is the root of our graph. So let's say the first approximation is here, that's x0. So what Newton-Raphson does is that you plug in x0 into Newton-Raphson, and the answer we get is basically the root of the tangent at that point. So when x equals x0, on the curve where x equals x0, the tangent that's formed at that point, that tangent crosses the x-axis at that point here. This is the value we get back from the Newton-Raphson formula. The formula is designed in such a way that it gives you the root of any tangent at any point on the curve, for whatever point you sub into the Newton-Raphson formula. So when x1 goes back into Newton-Raphson formula, it gives you where this tangent crosses the x-axis, and that becomes x2. And as you can see that the more times we iterate and more times we draw the tangent, the roots get closer and closer to the actual root where f of x equals to 0. Now, in our situation here, when x equals 0, what we get is a gradient of 0. So if the gradient is 0, so where x equals 0, we have a turning point in that case. So if we were to draw a tangent at our first approximation at 0, we get a horizontal line, and this line never crosses the x-axis, so we won't get another iteration of value from in that case. Another way of explaining this is to just look at the formula for the Newton-Raphson. Another way of explaining is f dash at 0 equals 0, and you can see here that in Newton-Raphson you end up dividing by 0. You get division by 0 in the Newton-Raphson formula. So there's two explanations. One explanation is that at x equals 0 you get a tangent that's parallel to the x-axis, which never crosses the x-axis. Therefore, we will not get a second iterative value. And another explanation is that f dash of 0 is 0, and in the Newton-Raphson formula, you're dividing by f dash of f dash, which means you're dividing by 0 in that case, which is not valid.